Okay, so as we've seen throughout this course, we really start to see a buildup of algebra, a very basic, different things happening, right? We first kind of start with geometry. Everything is focused on geometry. Everything is stated in terms of geometry and kind of stated in word problems in terms of areas of squares and volumes and this sort of thing, stuff like that. Or word problems in terms of taking bags of grain to this place and that place and stuff like that. And then eventually, starting around the beginning, the Middle Ages, as people were sort of going out and doing more commerce, there needed to be a better way to kind of talk about mathematics, and this is where more modern symbols came in. We went over that earlier in the semester. And so in the 18th century, that is to say the 1700s, algebra was still thought of as solving equations, and it's essentially what most people think about algebra today, or like what you would see in like a college algebra class, right? It's just about solving equations and maybe some things about functions and stuff like that. So during the 19th century, and starting a bit before that even, we'll get some citations from Gauss here in just a moment, it started to become less of that and more about the study of the mathematical structure of objects. Now, it's still connected to relating, it's all connected back to solving equations. So it's not like it's just completely separate things. And studying the algebraic structure or the mathematical structure of different algebraic objects, it wasn't just something that people were doing, for the heck of it or something. At least not initially. It was always connected to concrete problems that they were solving. Like, okay, well, we need to solve this problem, and actually, even though we care about this thing, we actually need to look at something slightly more abstract. Okay, so that's sort of the idea of what's happening. Okay, and so looking at these more abstract things and the structure of these abstract things led to solutions for for concrete problems. So, for example, if you want to talk about x squared minus 2, that polynomial, you have to go from the rational numbers to the irrational numbers if you want to talk about its roots. And as soon as you start doing something like that in an algebraic sense, all of these other things start to come into play, field extensions, etc., so on and so forth. Or if you want to think about x squared plus 1 is equal to 0, well, now you have complex numbers and all of the stuff that comes along with that. So looking at these more general mathematical objects or generalizations of known mathematical objects wasn't really started just like, oh, well, what if we generalize this or something like that. It's all connected to concrete problems. Okay, so various mathematical structures were introduced to generalize the integers. I, of course, mentioned that just a moment ago, but one of the ones that we'll talk about, which I think is most interesting, going to be the Gaussian integers. One of the reasons I think that's interesting is because this actually came up in a certain way before. Now, Gaussian integers are numbers of the form a plus bi. We would actually change this a little bit. Instead of I, we can look at a plus b times any sort of root, and get it, or any sort of new thing, and get a set of integers or set of an algebraic set that's similar to the Gaussian integers. But I'm not going to talk so much about that. Okay, so Gauss writes this book in 1798. So as you can see, this is 2 years before 1800, as we're starting to look at more general algebraic structures and things like that. So he introduces the modern notion of congruence. We've seen that many times throughout this semester. When we were looking at earlier versions of the Chinese remainder theorem, that's about solving systems of congruences. We talked a lot about that. We talked a lot about in that sort of few weeks in the class there, and so on. We talked about congruences, and so he says that A is equivalent to B mod M if M divides A minus B. Now this is something, again, it's something that we've seen before, but I used the notation then, but the notation didn't exist at the time of the people that we were studying. Gauss is the one that introduces it, and he introduces this 3-line notation because it's very suggestive. It looks like an equal sign, okay? So Gauss proves a lot of different basic properties about this. Essentially what he does is he proves that it's an equivalence relation, which isn't so difficult to see, but he also shows that most of the time, especially when p is prime here, all of the sort of algebraic things that you want to do to numbers, you can also do that to these numbers. So if you have two things that are equal, the things that do the same thing to both sides, this is going to work for this equivalence relation as well. So all the stuff that you want to do, algebraically and arithmetically with numbers, you can also do if you're just looking at numbers in this restricted sense. That is, if you're just looking at the congruence class of numbers modulo something. Okay, so one of the things that he proves, okay, is that p minus 1 factorial is congruent to minus 1 mod p. So one of the things that he proves is that p minus 1 factorial is congruent to minus 1 mod p. Okay, and I want to give an indication of why he did this, or not why he did this, but how he did this. So if we look at all of the congruence classes, so there are p congruence classes so p here is prime. There are p congruence classes mod p. Now, one of these is basically the zero congruence class. That is zero, the congruence class that contains 0 and p and other multiples of p. This is the zero congruence class. So if we just look at the other ones, 1, 2, 3, up to p minus 1, these form what's called a group under multiplication. So hopefully you know what a group is. If not, that's fine. You're probably going to want to look up what that is. Okay, so one of the things that this tells us, and I'm not going to show all of the background that goes into a proof like this. But one of the things this shows us is that if we do a to the power of p minus 1, no matter what a is, okay, if we do a to the power of p minus 1, this is congruent to 1 mod p. Now, this is known as Fermat's little theorem. It's also related to Lagrange's theorem in group theory as well. So there's many ways that you can prove this. I'm not going to give a proof, but there are many different ways that you can prove this. I remember when I was an undergrad, I had a homework assignment for one of my classes. There was basically just 5 different ways for proving Fermat's little theorem, and I thought it was a pretty interesting exercise. Maybe I'll put one of them. For the homework problem let's do next week. Anyways, or maybe I'll put it as a discussion question or something. So that's for any element. A to the power of p minus 1 is equal to 1. So if we know that a to the m is equal to 1 mod p, then what this tells us is that m must divide p minus 1. But there's actually, for every p, there are elements, so that a to the p minus 1 is equal to 1 mod p. That's true for all elements, but there is no smaller number. There's no smaller power with a to the m being equal to 1 mod p. Okay, so why does it help us prove this? So if you look at a number, a to the p minus 1 is equivalent to 1 mod p, and there's no smaller power that does this. Okay, there exists a number such that a to the p minus 1 is congruent to 1 mod p. Now this has different terms, but one of the things that we call it is a primitive root of unity, because a, you have to raise it to p minus 1 and no smaller power to get it to equal to 1. So p minus 1, again, if we're thinking in terms of group theory here, p minus 1 is the order of the group of the integers mod p under multiplication. And remember, that doesn't include 0 or multiple. multiples of p. Okay, so what this tells us then is that if you look at the elements A, let me write it like this actually. 1, what you're thinking about is being a to the power of 0, a squared, all the way up to a p minus 1. Well, each of these has to be a different element of, each of these has to be a different, in a different congruence class mod p. I know you guys think about that. So in other words, I'm saying each one of these is an individual, is a unique number mod p. So none of these numbers are equal to each other mod p, except I guess sorry. Haha, now it's true. Sorry about that. I got mixed up with where I wanted to end here. All of these numbers, a squared up to a to the p minus 1, these are all in different congruence classes mod p. Okay, I'm not going to prove that, but I want you guys to prove that. Okay, so now what does this tell us? So let me multiply them all out. So if we do a times a squared times dot 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 times a to the p minus 1. Well, then notice what we're going to do when we do this multiplication. We're simply going to add the exponents. So we're doing from the sum from 1 to p minus 1. Okay. Well, you know, there's another famous story about Gauss. That his teacher gave all the kids a assignment to do. It was a waste your time assignment. Add all the numbers up from 1 to 100. And there's different ways. There's sort of different stories on exactly how what happened. But Gauss realized if you start to pair up numbers, 1 and 101, or sorry, 1 and 100 makes 101. 2 and 99 makes 101, and you can do this all the way up to 50 times 51, and that's always going to be 101. So you can do this n over 2 times. If n is even, you can do this n over 2 times. There's n over 2 different pairs, okay? And then the sum is going to be n plus 1, 100 plus 1. Okay, so the sum from 1 to n is n times n plus 1 over 2. So here, n is equal to p, so it's going to be n, which is p minus 1, times n plus 1, which is p divided by 2. So this is a to the p over 2. Oops. A to the p over 2 times p minus 1. Okay, a times p over 2 to the p minus 1. Okay, so what this tells us is the following. That, well, this fact right here, so notice that p minus 1 is an even number. Forget about p is equal to 2. If p is a prime that's bigger than 2, let's forget about 2. We don't want to, that just sort of irritates, makes things irritating. So forget about the fake prime 2. If p is an odd prime, p minus 1 is even. So what this means is that since a to the p minus 1 is equal to 1 mod p, a to any lower power is not going to be equal to 1 mod p. Because that's sorry, let me say that a little bit differently. We're assuming that a is a primitive root of unity, so there's no power less than p minus 1, so that a to that power is equivalent to 1 mod p. So a to any power less than p minus 1 is not going to be equal to 1 mod p. Now, on the other hand, p minus 1 is an even number. So this means that a to the p minus 1 over 2, well, this is a to an integer. P minus 1 over 2 is definitely less than p minus 1. This is not equivalent to 1, but if we square it, sorry, let me see, make sure that's coming up okay. This is p minus 1 over 2. But notice that if we square this, we get a to the p minus 1. Okay, so what are the only two numbers whose square is equal to 1? Well, plus and minus 1 are the only two numbers whose square is equal to 1. Now, this is not equivalent to 1 mod p, so the only other option is that it has to be equivalent to minus 1 mod p. So a to the p minus 1 over 2 is equal to minus 1 mod p. Okay, so now what does that do for us over here? Well, this is going to be minus 1 to the power of p. So here I'm going to write the 3 bars because it means it's equivalent mod p. So you have minus 1 to the power of p, mod p. Okay, so this is equivalent to minus 1 to the power of p mod p. But p's odd, so minus 1 to the power of p just is equal to minus 1. And so in particular, this is equivalent to minus 1 mod p. All of these equivalences are mod p. All right, so overall, what it tells us is that this is equivalent to 1 mod p. This product is equivalent to 1 mod p. But every one of these elements is a distinct equivalence class, or it is in a distinct equivalence class. So all of these exhaust the integers p through p minus 1. So this product right here is equivalent to p minus 1 factorial, again, mod p. Okay, so what it shows, this is a very, what Gauss did was he was able to, generalize this notion of arithmetic to this modular setting, right? Kind of introduce new ideas and stuff like that, but he ends up proving this very concrete statement, that p minus 1 factorial is equivalent to minus 1 mod p. Now, this statement itself, p minus 1, another way to say this would be p divides p minus 1 factorial plus 1, okay? That statement has nothing to do, particularly with this sort of machinery that Gauss created to solve this problem, or more study of these algebraic objects and stuff like that. But we do see that it does help to have this these algebraic structures and to sort of generalize the idea of integer arithmetic to some setting like this to prove theorems such as this. Anyways, so that's going to be it for this video. We're going to look at some more Gauss stuff in the following couple of videos. At least one more video. I'm not sure how long that'll take.